With that then, I'd like to introduce our speaker. So welcome to the third day of FTQT. Our first speaker this morning is Gilles Zémor. Gilles is at the Bordeaux Mathematics Institute. He's done a lot of great work on quantum error correction. He has other work as well outside of quantum error correction. Everyone here knows his famous result with Tilings on these hypergraph product codes. And I think what he's going to tell us about today is some new extensions of this idea. And he's going to tell us about decodable quantum LDPC codes beyond the square root n barrier using high dimensional expanders. So please, Gilles.
Thank you very much. So thank you for the invitation and the privilege of speaking to all of you people. So I will try to progressively introduce the ideas that come with this construction. So let me start slowly with reminding you what are quantum CSS LDPC codes. Most of you, I guess, will be familiar with them, but to settle on notation and everything, it's a good idea to start with that. So the CSS code is defined by two binary matrices that we can call HX and HZ, and we can think of them as two classical error correcting codes if we come from the world of classical error correction. But the important point is that those two matrices need to have orthogonal row spaces, orthogonal in the binary field sense. So that's it, that's a quantum code. The dimension of the code is given by n, which is the number of columns of both matrices minus the length of the two matrices HX and HZ. And there are two minimum distances that we can call dx and dz, and they're defined as the minimum weight of a vector which is, say, orthogonal to the rows of x and not in the row space of hx, of the other matrix of hz. Similarly, we define the other distance dz, and the proper minimum distance of the quantum code is the minimum of those two x and z distances. And we're interested in the low density case in LDPC codes. This means that a requirement is that both our matrices HX and HZ need to be low density. And low density in a strong sense will mean we want a constant, we want the number of ones per row to be bounded from above by a constant, essentially, and with a similar requirement for columns. We can view exactly the same object as a chain complex. So in the general sense, this is just a change of vocabulary, nothing else. It means that we're viewing our matrices HX and HZ as linear operators. And these operators, we call them boundary or co-boundary operators. So we have three vector spaces, one vector space indexed by the columns of our matrices where the qubits sit, and the two other matrices, the two other vector spaces are indexed by the row space of our two matrices. And between them, we have boundary operators, and when we take their transpose, we have co-boundary operators. Homology groups for a complex are kernels of these operators divided by the image of the preceding operators. Elements of the kernel we call cycles, and the relevant objects are cycles which are not boundaries. These are the non-trivial cycles that we're looking at, and the minimum weight ones give the minimum weights, the distances that we've just defined for our quantum codes. So in the completely general case, it probably doesn't help all that much to have the chain complex viewpoint, but in many special cases it does help. And probably the mother of all quantum LDPC codes, the Kitaev toric code, fits this bill very well. So again, pretty much all of you will know how it works, but let me remind you. So our complex, we can think of it as this graph, this object, this grid, which is really a tiling of a torus. And the important point that we want to keep in mind is that it's an incidence structure with 3 objects, vertices, edges, and little squares that we can think of cells. So our 2 matrices, the incidence matrices of these little co-cycles for one, the squares for the other, and the dimension, the homology that comes with it is the homology, the F2 homology of the torus. It gives a code of dimension 2, and minimum distances, they're given by cycles which are not sums modulo 2 of boundaries of squares. Same thing for co-cycles, and we have this minimum distance that scales like a square root of n. That code, as you all know, has very many nice properties. It's been studied extensively. A couple of drawbacks is that it has a small dimension, which is only 2, and its minimum distance is just a square root of n up to a constant. And it's this completely open problem whether we can have quantum LDPC codes with substantially larger minimum distances. So what ideas do we have to get better complexes? I like to think that those ideas fall into a couple of categories. We have many geometrical approaches, and we have strategies where we will try to construct larger complexes from smaller ones, in particular product constructions. So examples of a geometrical approach, well, replace squares by pentagons, for example, and we'll be replacing a tiling of a torus by the tiling of a finite quotient of a hyperbolic plane. We get a graph which looks like this. This time the 2-dimensional objects are pentagons rather than squares. We get a dimension which scales linearly in n, but the minimum distance goes down to log n. Another idea is we can raise the dimension. For example, we could try and look at higher dimensional toric codes where the complex is really a cube. This time we have objects of larger dimensions, squares, and also little cubes. Qubits, we can put them on the squares rather than put them on the edges, and the 2-cycle will look like something like we have on the picture. So this idea has given several very interesting constructions of quantum LDPC code. Some relatively recent ones are by Boot and Lubotzky, where they use a tiling of hyperbolic force space. And there's this historic construction by Friedman, Mayer, and Lure, which has the record until recently for the minimum distance of a quantum LDPC code. It also uses clever tilings of some 4-dimensional manifold, and the minimum distance scales like square root of n times log n to the 1/4. So turning to these new complexes, one that we would like to introduce at this point is the LSV simplicial complexes, and they come from some quotients of affine buildings. So why am I introducing this complex? In a sense, it's sort of more complicated, less geometrical than the complexes that we've been discussing. What are its interesting points? So it's an incident structure. It's a simplicial complex, meaning the incident structure is between vertices, edges, and triangles. We can think of the object as a graph which is full of triangles. It has non-zero, it can be made to have non-zero homology, meaning that we can directly construct from it a quantum code, a quantum LDPC code with non-zero dimension. Now, this object has very special properties. In particular, it has very special links. So the link of a vertex, to get the link of a vertex, you take a vertex, you take all its triangles, and you take all opposing triangles. That gives you a graph. And the graph in our case is very special. It's the line point incidence graph of a projective plane over FQ. These graphs are sometimes called generalized hexagons, and among their many properties, there are very expanding graphs in the spectral sense. The second largest eigenvalue of their adjacency matrix is square root of Q, meaning essentially square root of the degree of the graph, which is very small and much less than half the degree of this graph. So why am I mentioning half the degree? Because I'm sorry, I'm just going to take 10 seconds. These graphs, I'm basically going to skip the next slide, which tells you that these graphs are actually very explicit. You can construct them with algebra, with a bunch of cleverly chosen 3x3 matrices. And this graph, so it's made up of patterns of smaller simplicial complexes that look like the one which is on the picture, but its degree is larger. And um, here I was going to remind you what the boundary functions look like in the simplicial complex case. So we have edge to vertex boundaries. When you have a bunch of edges, their boundaries are basically the endpoints. They're really the points that are hit an odd number of times by a set of edges. And we also have triangle to edge boundaries. When we have a bunch of triangles, their boundaries is what you can think of naturally. The edges that are hit an even number of times here in the middle go away. And we have similar objects for co-boundaries. Here we have a couple of vertices. Their co-boundaries are the set of red edges. Here, the ones that are hit twice disappear. And we also have edge to triangles co-boundaries that we'll be focusing on a little more. So this chain here has co-boundary these two red triangles that are the only ones that are hit once, meaning an odd number of times. Now, in this particular simplicial complex, the simple one, which is really the triangular tiling of the plane, the triangular lattice, if you will. The link of a vertex is a hexagon, if you remember the definition, and the hexagon is a graph whose second eigenvalue is exactly half the degree. Now, this LSV complex that I've been introducing, it has a second eigenvalue which is smaller than half of degree, and it's, believe me, super challenging to actually come up with such a simplicial complex. And the consequences of this fact are very far-reaching. One of the consequences is expansion in many in many senses. So one notion of expansion that is relevant to us is what several people have called Cosystolic expansion. And it means this: if you take a set of edges of size smaller than something, which is going to be linear in the total number of edges, and if you furthermore reduce your set of edges, meaning that you will add to it co-boundaries in the vertex-to-edge sense. So you add to it co-boundaries as long as you can reduce the weight, and when you can't reduce the weight, then you have a reduced set of edges. Now, Cosystolic expansion tells you that if you have a reduced set of edges of size smaller than something, which is actually linear in the total number of edges, then it has a large co-boundary. Its co-boundary is actually linear in its size. So this translates in particular into a very large x distance if you're thinking of the quantum LDPC codes that naturally comes with our two-dimensional simplicial complex. Because you see, it says that if if a pattern of edges were to have zero boundary and not be zero co-boundary, sorry, and not be a sum of vertex-to-edge co-boundaries, then if its size were smaller than something, it would necessarily need to have a non-zero co-boundary. So for a set of edges to be both non-trivial, not to be a sum of vertex-to-edge co-boundaries, and have zero co-boundary, then it needs to have a size which is linear in N. So the quantum code that comes with this complex has a very good x distance. Its z distance isn't so good. I'll go back to that in a minute. Furthermore, what we did in this recent work is show that it has the further property below, which is if you take a chain which is small enough, then you can always reduce its co-boundary by adding to it a small set of edges that sits inside the neighborhood of a single vertex. And this really gives you something is going wrong with my slide. Okay, so I was talking about decoding, so let me remind you what the decoding problem looks like, at least one version of it. So there's an x error vector that we can think of as a binary vector or a set of edges in our graph. You have to suppose that its weight is smaller than something, and what you actually given, what a measurement gives you, a quantum measurement gives you is a syndrome, which is exactly the same thing as a co-boundary, an edge to triangle co-boundary. And what you're trying to do is not find the x error vector exactly, which is not really going to be possible. You want to find an equivalent x error vector that has exactly the same co-boundary. An equivalent means that the sum of our two error vectors is a previous co-boundary, meaning a vertex-to-edge co-boundary. And the proposition that I've just discussed is that what will a decoding algorithm do? You will just look for a very small pattern of edges that sits inside the neighborhood of a single vertex. You might have to try different vertices to look for it. You look for error patterns that decrease the co-boundary. And you do this, you find a new co-boundary, you start again, you add a small error pattern that decreases the co-boundary until your co-boundary is 0, and you add up all the little error patterns that you've found along the way, and this is your equivalent error vector. That's the decoding algorithm, and we can prove that the weight of the original error is sufficiently small, and sufficiently small is still linear in the total number of edges in the length of the quantum code. Then the algorithm always converges and corrects properly. Now, all this concerns co-boundary, so X errors if you want. So we actually want quantum codes that will correct both X errors and Z errors. Now, this is the weak point of this complex. It can correct Z errors somewhat, but not many of them. This is in particular due to the fact that we're dealing with a graph there we have no boundary expansion, and it's only possible to guarantee a z distance that scales like a logarithm of n, like log n, which only gives you quantum minimum distance equal to log n, which is not so good. But the complex is something which is very special. If you take the product of both distances, the x distance and the z distance, you get n times log n. And all our previous examples that are much more balanced, at best they have both distances that scale like square root of n. And when you take their product, you find n, not n log n. And now you might want to think, can we somehow balance out those two minimum distance? Can we change the quantum code so as to keep this property that the product of the two distances is n times log n, and have both x and z distances more or less equal? And it turns out that this is possible. We can do this with a product construction. So how does the product construction go? It uses the picture that's on the screen, and we take a product of the simplicial complex that we've been discussing, VET, vertex, edge, T incident structure, with a more ordinary bipartite graph, AB, which should be an expanding bipartite graph to give a good result. And the incidence, the incident structure is defined like it's suggested on the picture, meaning that a couple EA is going to be incident to a couple TA in the product, if and only if E is incident to T in the original simplicial complex, and so on. And we have exactly 5 types of edges of this sort. And what happens if we look at this construction closely is that the x distance of the new complex is going to be unchanged instead of the original simplicial complex, and the z distance actually grows. It's multiplied by the classical minimum distance of the classical code that is described by the AB bipartite graph. So by choosing parameters properly, we can make the z distance, we can boost it, we can make z distance as good as the x distance in the new complex. And what happens when we look at everything closely is that we will eventually get a minimum distance, which is what was announced, which is square root of n times log n in this particular case. So this balancing idea originates with the paper from Hastings, who studied the special case when the AB bipartite graph is a path. And this product construction, if you're familiar with the product construction that's we described with Tilings and that you mentioned in the introduction, if the original complex were really one-dimensional, in the sense if there were no V's, then this VA part would disappear, and what we would have is exactly the TZ hypergraph product construction, of which this is therefore a generalization. So we can do some variations with these ideas. So one variation is to raise the dimension of the original LSV complex. So what can we do? We can start with a 3-dimensional LSV complex, which is an incident structure between 4 objects instead of 3 objects: vertices, edges, triangles, and tetrahedra, which we'll call pyramids because tetrahedra also starts with a T. And we can do 2 things. We can forget the pyramids and again have a VET simplicial complex, or we can forget the vertices, the vertex set, and take the subcomplex ETP, which is really 2-dimensional general chain complex, but not the 2-dimensional simplicial complex. So this incident structures I've tried to explain at the beginning, it immediately translates into the quantum code. And I'm, from the point of view of the minimum distance, this quantum code will actually be better. It will again have non-zero dimension. It will again, for essentially the same expanding reasons, have an x distance which is linear in n, and it will have a slightly better z distance, which will scale like the square of the log of n instead of the log of n. In a few words, I can try and give an idea where this log of n squared comes from. The thing is that to get a handle on the z distance, we use injectivity radius arguments. If you remember these, maybe haven't said it, but these finite simplicial complexes, they're obtained from taking quotients of infinite objects where there's no homology. And what happens is, inside of sphere of sufficiently small radius, and that's what the injectivity radius is, it's the smallest radius for which spheres inside the infinite complex and inside the finite version are exactly the same. And as long as you're inside balls of radius smaller than the injectivity radius, then homology can't appear. You can't have cycles that are not sums of boundaries. Now, in the previous 2-dimensional simplicial complex case, cycles were just ordinary cycles in the graph sense. Here, cycles locally may look like something which is on the picture. And this drawing actually is part of a subgraph, special subgraph called apartments of LSV complexes that really actually look like tilings by triangles of Euclidean planes. And the point is that when the number of triangles inside the apartment, it grows like the square of the radius, hence the log n square for dz. What one can show is that the cycles that locally grow as slowly as possible, they will always, well, you can't do worse than what you have if you take your cycle inside an apartment. This is what happens. So again, if we use the distance balancing strategy, you have again a quantum LDPC code, this time with a slightly larger minimum distance, which is square root of n times log n instead of square root of n times square root of log n that we had before. And this is the current record as far as minimum distances are concerned. When we do this, there's some things that we lose. This time, we have a decoding problem. We don't know how to decode from boundaries. We don't know how to decode from Z errors, and this is because we don't know how to decode from Z errors in the component subcomplex of our three-dimensional simplicial complex. This time, the boundary function is more complex than the boundary function in the previous case, and we don't have this very nice co-boundary expansion. We don't have boundary expansion, and devising a decoding strategy in this case is a challenge. At this point, we don't know how to do it. So I think it's time for me to conclude. So the last slide with some takeaways. If we did the same thing, started from higher dimensional LSV complexes and taking a subcomplex which is further and further away from the original complex, so we throw away vertices, we throw away edges, and so on, we would possibly obtain quantum codes with a minimum distance which scales at least like n, sorry, it should be square root of n, times a power of log n, a larger power of log n than the one we currently have. All the same arguments would work, except that it's not clear whether these subcomplexes of the multidimensional LSV complexes would have non-zero homology. If it were possible to prove that, then we would have these slightly larger distances. And by the way, these distances are low bounds. It's not clear whether they really are going to be exact or not. As I've just mentioned, so decoding from boundaries is always going to be an issue for these complexes. The weak point of these LSV complexes is the boundary function, which doesn't give you expansion and translate into comparatively smallish Z distance bounds. And I haven't talked, because I didn't have time, about the complete decoding strategy for the whole quantum code, which comes with this product complex. I'll just mention that it rests upon decoding the component complexes in the way that I've tried to describe, and some linear algebra, which I'm not going to describe. I think it's time for me to stop. I'm probably over time. If so,
that's okay. We had a couple of interruptions. So thank you, Gilles, for the wonderful presentation. We already have a couple of questions in the Q&A. So there's a couple that are really short. Ani Krishna is asking, is K expected to be arbitrarily large, or is there any cap on K?
So by K, do you mean the dimension, or do you mean the K on this slide?
I believe he means the power of log n
of the log.
In that slide, yeah.
With this conjecture on the homology of these complexes, there's pretty much, yeah, there's no upper bound on the size of k, except that what's not really apparent is that when you raise the dimension like this, you're also raising the size of the complex. So n is really going to be larger and larger. So maybe your question is, can we get k to be a function of n, and eventually get something which is k could be maybe not fixed.
Right. Yeah, I was just wondering if it was bounded by the size of the dimension, or if it could somehow grow with n.
Well, by the dimension, you mean the dimension of the complex? Yeah,
Yes.
it grows with the dimension of the complex. So to get +1 on k, you need to +2 on the dimension of the LSV complex.
Okay. Thank you.
It works like this.
Right. A couple more questions. Thomas Joachim O'Connor writes, if you generalize this to higher dimensions, does this imply a trade-off with the encoding rate of the code?
Not really, because the dimension of the quantum code, I'm assuming this is really what you mean by the coding rate. So the dimension of all these quantum codes is going to be very close to square root of n.
Right. I think he's asking in the two-dimensional example that you showed,
yes,
the rate was square root of n divided by square root of log n. Or sorry, the not the rate, but the
dimension.
The dimension, and but then you were able to increase the log factor in the distance from square root of log n to log n. Does the rate continue? Sorry, does the dimension continue to go down and increase the distance?
Yeah, the dimension gets closer and closer to square root of n, but not more, unfortunately.
Okay. And then I guess we have time for one more quick question. And maybe we need to just unmute Andrew because he wrote a paragraph in the Q&A. Can one of the panelists? There we go. Okay, Andrew.
Okay, can you hear me?
Yes.
I'll ask it more briefly, perhaps. These codes are great, but a question I'm wondering about is what dimension in Euclidean space is required to embed these, say, 2D LSV complices in when you do a hypergraph product of them with some sufficiently expanding bipartite graph. My question is sort of, getting at, well, how might you eventually realize this in hardware someday by taking whatever Euclidean space embedding you have and projecting it down to some low-dimensional Euclidean space?
Honestly, I have no idea.
Okay. Do you know if it's exponential in n, the dimension of Euclidean space you embedded in, or is it polynomial in n?
I don't know. I haven't asked myself this question at all, and it's I don't think it's a standard question for LSV complexes, and it sounds like a pretty tough question. Yeah, I'm sorry, I can't say.
Okay, thanks. Well, I think a lot of us would be excited about building something like this. So it's something I think that's a question that a lot of us are wondering about. Thanks.
And I'm just going to have one last question, which is, do you think that there are going to be any upper bounds on the minimum distance of stabilizer quantum LDPC codes? Or do you think we can achieve distance proportional to n?
I don't know. I mean,
I don't
it's
think anybody
so, depending on what sort of day it is when I wake up, I change my mind.
Okay.
Mostly, I would like to think that quantum LDPC codes with large minimum distances, meaning possibly all the way up to linear in n, exists, because I want them to exist, and also because I don't see why they shouldn't exist. But I mean, of course, I could be completely wrong. So
Right. Well, we should, yeah, we all have this optimism bias, don't we? Or else we couldn't have survived in research. So let that be an open challenge to everybody listening. Go prove or disprove quantum LDPC stabilizer codes with good minimum distance. It's a great open problem. So with that, we should close the session. Thank you, Gilles.